Hello everyone. Today we will study general combination. Before I introduce what it is, let's look at some simple example first. Before I introduce what it is, let's look at some simple example first. First example, part A. Consider an equation x1 plus x2 equal to 6. With both s1, x2 greater or equal to 1. How many integer solutions are there? Consider this equation. S1 plus S2 equal to 6, with both S1 and S2 greater or equal to 1. How many integer solutions are there? Let's try to get an answer first. Let's try the answer out first. Can we try? S1, S2 must be greater than 1. So one of the solution I can use 1 and 5. 1 plus 4 is 6. Another possibility could be 2 and 4. Or I can try 3 and 2. S1 is 3, S2 is X. S1 is 3, S2 is 2. Or we can try 3 and it should be 3 and 3. Or I can try 4 and 2. 5 and 1. So by trial and error, we find 5 solutions. So there are 5 solutions. We get this by trial and error. We get a solution by trial and error. Part B. For the equation S1 plus S2 plus X3 equal to 6, with S1, S2, X3 greater or equal to 1. How many integer solutions are there? For this equation, S1 plus S2 plus S3 equal to 6, with S1, S2, S3 greater or equal to 1. How many integer solutions are there? Can we try that out? This is not easy to try. Let's try. S1. Can we try that out? S1, S2, X3. By trial and error, what can we get? We can have 1, 1, 3. That's one possibility. 1, 1, 3. We may have 1, 1, it should be 1, 1, 4. Total is 6, it should be 1, 1, 4. We may have 1, 2, 3. we may have 1, 3, 2. We may have 1, 4, 1. We may have 2, 1, 3. Two, 2, 2. 2, 3, 1. Or we may have 3, 1, 2. 3, 2, 1. Or we may have 4, 1, 1. So by trial and error, we get 10 solutions. So by trial and error, we get 10 solutions. For small number, we can get an answer by trial and error. But is there a better way to get a solution other than trial and error? Is there a better way to get an answer other than trial and error? Let's consider this. S1 plus S2 equals 6. S1, S2 must be whole numbers. Consider there are 6 objects. Consider there are 6 objects. For the first problem, consider there are 6 objects. 1, 2, 3, 4, 5, 6. I try to in order to find solution for S1, S2, I try to separate these 6 objects into 2 groups. In order to find solution for S1, S2, I try to separate these 6 objects into 2 groups. If I put a bar here, I separate this object into 2 groups. If I put a bar here, I separate this 6 objects into 2 groups. First group has 1 object. Second group has 5 objects. That's one of the solution. S1 is 5. S1 is 1. S2 is 5. Now, if I put a bar here, that's another solution. That means my first group, S1, is 2. S2 is 4. If I put a bar here, that's another solution. S1 is 3. X2 is 3. If I put a bar here, that's another solution. S1 is 4. S2 is 2. If I put a bar here, S1 is 5. S2 is 1. So as long as I put a bar in the middle of these 6 objects, I have a solution for S1, S2. As long as I put a bar in the middle of these 6 objects, I find a solution for this pair of S1, S2. So in how many ways can I put a bar in the middle? For 6 objects, there are 5 gaps between 6 objects. I can put my bar here, 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 here. So I have 5 ways to put a bar. I can write it as combination. 5, choose 1. I can choose 1 gap here to put a bar in the middle. I can choose 1 gap out of 5. I can choose 1 gap out of 5 to put a bar later. Whenever I put a bar, I find a solution for S1, S2. If I put a bar here, my S1 is 2, S2 is 4. Whenever I put a bar between the gap of 2 objects, I find a solution. So the number of solutions is 5, choose 1. I can put my bar in one of these 5 positions, which is 5, choose 1. And we know 5, choose 1 is 5. Let's match this 5 solution here. Consider the second problem. S1 plus S2 plus S3 equal to 6. Think of the problem the same way. I have 6 objects. 1, 2, 3, 4, 5, 6. I try to separate these 6 objects into 3 groups. In order to separate it into 3 groups, I need to put 2 bars in the middle. In order to separate 6 objects into 3 groups, S1, S2, S3, I must put 2 bars in the middle. So whenever I put 2 bars in the middle, I find a solution. So for example, if I put 1 bar here, 1 bar here, there's 1 object here, my S1 is 1. There's 1 object here, my S2 is 1. There are 4 objects here, my X3 is 4. So there are 3 solutions. There is this solution 1, 1, 4. S1 is 1, S2 is 1, X3 is 4. If I put my bar here, that means my S1 is 1, there's 1 object here. My S2 is 2. My X3 is 3, there's another solution. So as long as I put 2 bars in the gap of these 6 objects, I find a solution to this equation. As long as I put 2 bars in the gaps of these 6 objects, I find a solution to this equation. There are 6 objects. How many gaps are there? There are 6 objects. How many gaps are there? We have 1 gap, 2 gaps, 3 gaps, 4 gaps, 5 gaps. For 6 objects, we have 5 gaps in the middle. In order to find a solution for 3 variables, I need to separate it into 3 groups. In order to separate a set into 3 groups, I need to cut it twice in the middle. So there are 5 gaps. I try to choose 2 positions to put the bars. There are 5 gaps. I try to choose 2 positions to put the bars. As long as I put 2 bars there, I find a solution to this equation. So there are 5 gaps in the middle. There are 5 gaps in the middle of 6 objects. I want to choose 2 positions to put bars. That's 5 choose 2. Whenever I put 2 bars here, I find a solution to S1, S2, S3. So 5 choose 2 is 5 factorial over 5 minus 2 factorial over 2 factorial. Numerator is 5 times 4 times 3 times 2 times 1. Denominator 5 minus 2 is 3. 3 factorial is 3, 2, 1. 2 factorial is 2 times 1. Cancel 2 times 1. 3 and 3 get cancelled. 4 divided by 2 is 2. 5 times 2 is 10. So that's how we get 10 solutions. That's how we get 10 solutions by using combination. In general, for large numbers, we can't get answer by trial and error. In general, for large numbers, we can't get answer by trial and error. Part C. For the equation S1 plus S2 plus plus x sub n equal to R, where R is greater than n, and each x is greater or equal to 1. How many integer solutions are there? How many integer solutions are there? So for this problem, we can use the same approach. Consider there are objects. Consider there are objects. We try to find integer solution for S1, S2 up to Sn. That means I try to separate this R object into n groups. We try to separate R objects into n groups. We try to separate R objects into n groups. If I try to separate this object into two groups, I cut it once. I put one bar in the middle. If I try to separate this into three groups, I put two bars in the middle. Here, since we are looking for solutions for S1, S2, S3 up to Sn, we try to separate this R object into n groups. If I try to separate this into n groups, I need to put m minus 1 bar in the middle. I need to put m minus 1 bar in the middle. And how many gaps are there? For R objects, how many gaps are there? For 2 objects, we have 1 gap. For 3 objects, we have 2 gaps. For 4 objects, we have 3 gaps. So for R object, we have R minus 1 gaps. So there are R minus 1 gaps. We try to choose m minus 1 gaps and put a bar there. So the number of solution is m minus 1, choose m minus 1. The number of solution is R minus 1, choose m minus 1. This is combination. R minus 1, choose m minus 1. There are totally R minus 1 gaps for R objects. We are looking for solution for nx here. We are looking for solution for nx. That means I need to separate R objects into n groups. In order to separate R object into n groups, I need to put m minus 1 bar in the middle. I need to put m minus 1 bar in the middle. So I choose m minus 1 bar out of R minus 1. Order doesn't matter. I choose m minus 1 position out of R minus 1 and put a bar later. I separate it into n groups, and that's a solution for this equation. Since I can find a solution in this many ways, it has this many solutions. So that's an answer. Next, part D. For the equation S1 plus S2 plus X3 equal to 6, with S1, X2, X3 greater or equal to 0, how many integer solutions are there? How many integer solutions are there? Now, if S1, S2, X3 is greater than 0, how can we find a solution here? If we compare this problem with the previous problems, we can see that they are almost the same. They are almost the same equation. The only difference is that for the previous problems, the x are greater than 1. Here, x, the variables, are greater or equal to 0. What can we do for this problem? For this problem, let's think of this way. We try to choose some variable, make it greater than or equal to 1. So let's do the following substitution. Let y1 equal to s1 plus 1. Let y2 equal to s2 plus 1. Let y3 equal to x3 plus 1. Then what do we have here? Since x1 is greater than or equal to 0, then y1 will be greater or equal to 1. Since x2 is greater or equal to 0, then y2, since x2 is greater or equal to 0, then y2 will be greater or equal to 1. 0 plus 1 is 1. Since x3 is greater or equal to 0, then y3 will be greater or equal to 1. Now, how can we change in this equation, how can we change x to y? How can we change x to y? For each equation here, I can solve x and write x in terms of y. If I solve each equation for x, what do I get? If I solve the first equation for s1, I have s1 equal to y1 minus 1. If I solve the equation for s1, I have s1 equal to y1 minus 1. s2 equal to y2 minus 1. x3 equal to y3 minus 1. Then I can substitute each x into the original equation. I have y1 minus 1 plus y2 minus 1 plus y3 minus 1 equal to 6. Then if I simplify this equation, I can make y1 plus y2 plus y3 minus 1 minus 1 minus 1, that means minus 3 equal to 6. So this equation can be rewritten as y1 plus y2 plus y3 equal to 9. How many integer solutions here? How many integer solutions do we have here? The number of integer solutions using the previous formula, we have 3 variables. So n is 3. We have 3 variables, y1, y2, y3. So n is 3. And the sum is 9. The sum is 9. That means R represents 9 here. Here R is 9. If I use this formula, replace R with number 9, replace n with number 3, I have the number of integer solution. The number of integer solution is 9 minus 1. Choose 3 minus 1, which is A choose 2. And A choose 2, use calculator, that's 28. There are 28 integer solutions for y. We have 28 integer solutions for y. And then we know that for every integer solution for y, we can find an integer solution for x. It's a one-to-one correspondence. For every integer solution for y, I can find integer solution for x. So since there are 28 integer solutions for y's, since there are 28 integer solutions for the y's, it should be 28 integer solutions for the x. So the answer is 28. Since there are 28 integer solutions for the y's, it should be 28 integer solutions for the x. Next, let's look at a more general case. For the equation s1 plus s2 plus xn equal to r, with r greater or equal to 0, and each x, s1, s2, up to sn, are greater or equal to 0. For this equation, how many integer solutions are there? If we compare this problem with the previous problem, the problems are almost the same. The only difference is that for the previous problem, each x is greater than 1, greater or equal to 1. In this problem, each x is greater than or equal to 0. That's the only difference. So we try to make substitution, make each variable greater or equal to 1. in order to find a solution, we try to make substitution, make each variable greater or equal to 1. Then I can use this formula to find a number of solutions. So the same as previous problem, I make substitution. Let y1 equal to s1 plus 1, y2 equal to s2 plus 1, and in general, let yn equal to sn plus 1. Then, since each x is greater or equal to 0, x plus 1 will be greater or equal to 1. Then each y will be greater or equal to 1. y1 will be greater or equal to 1. y2 will be greater or equal to 1. And yn will be greater or equal to 1. Next, I try to get x by itself. X can be rewritten as y1 minus 1. S1 is y1 minus 1. S2 is y2 minus 1. And in general, Sn is y sub m minus 1. Then I can substitute each x into the equation here. If I substitute each x into the equation, I have y1 minus 1 plus y2 minus 1 plus, in general, we have ym minus 1 equal to r. Then if I simplify the equation, I can write it as y1 plus y2 plus yn. We have negative 1 n terms. There are n terms negative 1. So added together, that's negative n equal to r. Next, I try to move the constant n to the other side. I can rewrite this as y1 plus y2 plus y sub n equal to m plus r. If I add n to both sides, I get this equation. Then this equation is very similar as this equation. Each variable in the equation must be greater or equal. Each variable in this equation is greater or equal to 1, and there's a sum here. Then apply this formula. M plus r actually represent r in this equation. M plus r represent r in this equation. There are n variables, so this n is the same as this n. This n here is the same as this n. But this r here represent m plus r in this equation. This r represent m plus r in this equation. So the number of integer solution to this equation is m plus r minus 1 choose m minus 1. The number of integer solution to this equation is m plus r minus 1 choose m minus 1. Because in this equation, m plus r represent r in this equation. I substitute, plugging m plus r for this r here. I have m plus r minus 1 choose m minus 1. This n is the same as this n. This n represents number of variables. It's the same as this n. There are n variables in this equation, and we also have n variables in this equation. So we have this many solutions for y's. We have this many solutions for the y's, but the difference of x and y is 1. For every solution for y, I can find a solution for x. So we have the same number of solutions to the x and y. Since we have this many solutions to y's, we also have this many solutions to the x. So keep this in mind. Note. The number of integer solutions to the equation S1 plus S2 plus n equal to R, with R greater equal to n, and S1, S2, Sn greater equal to 1 is R minus 1 choose m minus 1. Combination R minus 1 choose m minus 1. The number of integer solutions to the equation S1 plus S2 plus Sn equal to R, with R greater equal to 0 and each x is greater equal to 0 is the number of integer solution to this equation is m plus R minus 1 choose m minus 1, or this formula can be rewritten as m plus R minus 1 choose R. These two formulas are equivalent. Do you remember why? Last class I showed you a formula that for combination n choose R is the same as n choose m minus R. That's what I showed you last class. So for this combination here, m plus R minus 1 choose m minus 1. If I treat this as n, I treat this as R, what do I have? I have m plus R minus 1. The top stays the same. From the bottom we use top minus bottom. M plus R minus 1 minus m minus 1. If we subtract, we have n plus R minus 1. On the bottom, m minus n, we have m plus R minus 1 minus m plus 1. M minus n can cancel. Negative 1, positive 1 can cancel. What's left is R. So that's m plus R minus 1, choose R. They are exactly the same. That's the theorem we learned last class. Based on this theorem, these two expressions, they are exactly the same. So the number of integer solution to this equation is either this, or I can write it in this way. That looks a little simpler. Than this. Either way is okay. Next, let's look at another example. Assume there is a large amount of color marbles. Assume there is a large amount of color marbles, say blue, yellow, and red marbles. When 6 marbles are chosen, from the set. How many different combinations are there? For combination means order doesn't matter. We don't care which marble I choose first. I care what marble we choose. So when 6 marbles are randomly chosen from the set, how many different combinations are there? We may have 1 blue, 2 yellow, 3 red, or 4 blue, 1 yellow, 2 yellow, 0 red. How many different combinations are there? Let's do this. Assume X1 blue marbles are chosen. Assume S1 blue marble, S2 yellow marble, and X3 red marbles are chosen. Then, since we are choosing totally 6 marbles, then S1 plus S2 plus X3 will be 6. And each X must be greater or equal to 0. We cannot choose negative number of marbles. We need to choose at least 0 marbles. 0 of each marbles. So S1, S2, S3 must be greater or equal to 0. The number of solution to S1, S2, S3 is the number of combination to this set. The number of solutions to S1, S2, S3 to this equation is the number of different combinations for the marbles. So by the previous theorem, we know that for the equations S1 plus S2 plus Sn equal to R with R greater than 0, S1, S2, Sn greater than 0. The number of integer solution is n plus R minus 1, choose n minus 1. So also, the number of integer solutions to this equation if we use the formula that is m plus r minus 1, 3 plus 6 minus 1, m plus r minus 1. Choose m minus 1 or choose r. You can use 3 minus 1 or you can use 6 here. It's the same. The number of integer solution to this equation is m plus r minus 1. Choose m minus 1. m plus r minus 1. Choose m minus 1. The number of solutions to this equation is a choose 2. And use your calculator, a choose 2 is 28. So there are 28 integer solutions to this equation. That means we have 28 different combinations for the marbles. Since the number of integer solutions to the equation is the same as the number of different combinations for the marbles. Then we know that there are 28 different combinations. There are 28 different combinations for the marbles. Next, let's look at a more general case. Assume there are n categories of objects. Assume there are n categories of objects with infinite supply. When R objects are chosen, how many different combinations are there? When R objects are chosen, how many different combinations are there? So we can solve it in a similar way. Assume X1 objects from the first category X2 objects from the second category and Xn objects Sn objects from the n category are chosen. Assume S1 objects from the first category, X2 objects from the second category, and Sn objects from the n category are chosen. Then, if we add them up, S1 plus S2 plus Sn must be R, because we totally choose R objects. S1 plus S2 plus Sn equal to R. And each X, we must choose at least, we cannot choose negative number of items, so each X must be greater or equal to 0. We may choose 0 element. We may choose 0 element, but we cannot choose negative elements. So each X may be greater or equal to 0. And we know that the number of solutions to this equation the number of integer solutions to this equation. So the number of integer solutions to this equation is m plus r minus 1 choose m minus 1. So there are m plus r minus 1 choose m minus 1 different combinations. This is the general combination. Let me give you the rule here. Combination with repetitions the number of ways to choose are objects out of n category with infinite supply. Is m plus r m plus r minus 1 choose m minus 1 or m plus r minus 1 choose r, denoted by double parentheses n choose r. It's that n multi choose r. It's that n multi choose r. So keep this in mind. Keep this notation in mind. N multi choose r, choosing r objects out of n category. M multi choose r, we are choosing r objects out of n category is m plus r minus 1 choose m minus 1 or m plus r minus 1 choose r. That's the formula for combination with repetitions. Next, let's look at some simple examples. In how many ways can we choose a dozen of donuts from the 10 varieties in a donut store, in a donut shop. In how many ways can we choose a dozen of donuts from the 10 variety in a donut shop? So here, if there are 10 varieties, we assume there are 10 different categories of donuts, and for each category, we have infinite supplies. So we try to choose a dozen of donuts. A dozen of donuts means 12 donuts. We try to choose 12 donuts out of 10 categories with infinite supplies. We try to choose 12 donuts out of 10 categories with infinite supplies. So use the formula, we have 10 multi-choose 12. There are totally 10 categories. We choose 12 objects out of 10 categories. 10 multi-choose 12. If we use the formula, that's 10 plus 12 minus 1. Choose 10 minus 1, which can be rewrite as 10 plus 12 is 22. 22 minus 1 is 21. 21 choose 9. That's combination. 29 choose 1. You can use a calculator to get an answer. Next example. In a store, there are 4 different types of fruits. There are 4 different type of fruits. In how many ways can someone buy 8 fruits? Suppose there are 4 different types of fruits. In how many ways can someone buy 8 fruits? So assume we have 4 different categories, 4 different types of fruits. Assume we have 4 different categories of fruits with infinite supplies. There are 4 different categories. We are choosing 8 fruit out of 4 categories. We are choosing 8 fruits out of 4 categories. That's 4 multi-choose A. That's 4 multi-choose A. If we use the formula, we have 4 plus A minus 1. Choose 4 minus 1. M plus R minus 1. Choose M minus 1, which is 11 choose 3. And you can use your calculator to get an answer. This is combination, 11 choose 3. Next example. In a vendor machine, there are 12 kinds of drinks. There are 12 kinds of drink, including Sprite, Pepsi, and Mountain Dew. A teacher would like to buy 8 drinks for his student. First question. How many different combinations does he have? How many different combinations does he have? So we have 12 kind of drinks. That means there are 12 categories. He only buy 8 drinks. So he buy 8 drinks out of 12. That's 12 multi choose A. That's 12 multi choose A. If we use the formula, that's 12 plus A minus 1. Choose 12 minus 1. 12 plus A minus 1. Choose 12 minus 1. Which is 19 choose 11. Use your calculator, you can get an answer. There's a number of different combinations he has. Part B. If he does not want any Sprite, if he doesn't want any sprites, if he does not want any Sprite, then how many different combinations does he have? If he doesn't want any Sprite, how many different combinations does he have? There are 12 different categories. Sprite is one of the category. If he doesn't want any Sprite, means he exclude one of the category. If he doesn't want any Sprite, means he exclude one of the category. There are 11 categories available. There are 11 categories available. From the 11 category, he buy 8 drinks. He choose 8 objects. From 11 category, he choose 8 objects. So the answer is 11 plus A minus 1. Choose 11 minus 1. 11 plus A is 19. 19 minus 1 is 18. 11 minus 1 is 10. So that's 18 choose 10. Use your calculator. Be very, very careful. 18 choose 10 doesn't mean 18 divided by 10. This is combination. This is 18 factorial. 18 minus 10 is A factorial times 10 factorial. 19 choose 11 doesn't mean 19 divided by 11. Be very, very careful. That's 19 factorial. 19 minus 11 is 8 factorial times 11 factorial. This is combination, it's not division. Be very, very careful. Part C. If he wants exactly one Pepsi, if he wants exactly one Pepsi, how many different combinations can he have? If he wants exactly one Pepsi, how many different combinations can he have? He's buying 8 drinks. 1, 2, 3, 4, 5, 6, 7, 8. He's buying 8 drinks. If one of them must be Pepsi, let's make choice for Pepsi first. If we buy one Pepsi first, then he need to buy 7 more drinks. If we buy one Pepsi first, he need to buy 7 more drinks. And for these 7 more drinks, he doesn't want any Pepsi. For these 7 more drinks, he doesn't want any Pepsi. So that means for these 7 drinks, there are 11 categories available. For these 7 drinks, there are 11 categories available. And he wants to buy 7 more drinks. He wants to buy 7 more drinks out of 11 category. He buy a Pepsi first. Since he wants exactly one Pepsi, so he buy one Pepsi first. Then he has 7 choice left. He has 7 more drinks left. Then since he buy one Pepsi already, he wants exactly one Pepsi. That means he doesn't want any more Pepsi. So Pepsi is out of his choice. For these 7 drinks, he buy these 7 drinks out of 11 category. This Pepsi is not available for these 11 drinks. There are 11 categories for these 7 drinks. So from 11 category, he buys 7 drinks. He chooses 7 objects. That's 11 multiplied to 7. Use formula 11 minus 7, 11 plus 7 minus 1. Choose 11 minus 1, which is 17, choose 10. Use your calculator. That's 17 factorial over 17 minus 10 is 7. 7 factorial times 10 factorial. Use your calculator, you can get an answer. Part D. If he wants at most one Pepsi, how many different combinations can he have? If he wants at most one Pepsi, how many different combinations can he have? At most one Pepsi means either he chooses no Pepsi or he chooses one Pepsi. There are 2 cases. Either he chooses 0 Pepsi or he chooses one Pepsi. That's what at most one Pepsi means. At most one Pepsi means either he chooses 0 Pepsi or he chooses one Pepsi. If he chooses 0 Pepsi, means Pepsi is not available. He cannot choose any Pepsi. There are 11 categories. Pepsi is one of the category, but he can't choose any Pepsi. So he chooses from 11 categories. He chooses 8 drinks, 8 objects from 11 categories. He chooses 8 objects out of 11 categories. All 8 drinks cannot be Pepsi. So Pepsi is not one of the category here. He cannot choose from Pepsi. Or if we choose one Pepsi, pick the Pepsi first, then he choose 7 more drinks out of 11 category. Pick one Pepsi first. If we choose one Pepsi, pick one Pepsi first, then choose 7 more drinks out of 11 category. That's 11 multi choose 7. Then use formula. That's 11 plus 8 minus 1. Choose 11 minus 1 plus 11 plus 7 minus 1. Choose 11 minus 1. That's 18. Choose 10. Plus 17. Choose 10. And then use your calculator. You can get an answer. This is combination. Not fraction. Use your calculator. You can get an answer. Part E. If he wants exactly 2 Mountain Dew Dews and 1 Pepsi, and at most 1 Pepsi, if he wants exactly 2 Mountain Dews and at most 1 Pepsi, how many different combinations can he have? If he wants exactly 2 Mountain Dews and at most 1 Pepsi, how many different combinations can he have? So he's buying 8 drinks. He wants exactly 2 Mountain Dews. So now he picked 2 Mountain Dew first. So he picked 2 Mountain Dew first. Then he has 6 drinks left. Mountain Dew is no longer available. He picked 2 Mountain Dew already. Mountain Dew is not one of his choice anymore. So he needs to choose 6 more drinks. But Mountain Dew is out of his choice. Now, at most 1 Pepsi, that means there are 2 cases. Either he choose 0 Pepsi or he chose 1 Pepsi. If he choose 0 Pepsi, that means for these 6 drinks, he can't choose Mountain Dew, he can't choose Pepsi. There are 10 different categories left. If he choose 0 Pepsi, that means for these 6 drinks, he can't choose Mountain Dew, he can't choose Pepsi. So there are 10 different categories. Left, and he needs to choose 6 more drinks. Or if we choose 1 Pepsi, then he choose this one. He pick 1 Pepsi here. Then Pepsi is no longer available. Once he chooses Pepsi here, Pepsi is no longer available. He can't choose any more Pepsi. And he can't choose any more Mountain Dew. Since Mountain Dew and Pepsi are not available, there are 10 different categories left. And he needs to choose 5 more drinks. He needs to choose 5 more drinks. So that's 10 multi choose 5. Then use the formula. 10 multi choose 6 is 10 multi choose 6 is the combination 10 plus 6 minus 1. Choose 10 minus 1. 10 multi choose 5 is the combination 10 plus 5 minus 1. choose 10 minus 1. Then multiply out. 10 plus 6 minus 1 is 15. 10 minus 1 is 9. 10 plus 5 minus 1 is 14. 10 minus 1 is 9. Then use your calculator, you can get an answer. Use your calculator, you can get the exact answer. Part F. If he wants at least one Sprite, how many different combinations does he have? We know that he need to choose a total of 8 drinks out of 12 categories. In order to guarantee at least one Sprite, he need to pick one Sprite first. So pick one Sprite first. Then he need to choose 7 more drinks. How many categories are available? Since he may have more than one Sprite, since he may choose more than one Sprite, so Sprite is still a possible choice for him. Therefore, the number of ways to choose 7 more drinks is 12 multi choose 7. Since Sprite is still a possible choice for him, we have the number of ways to choose 7 more drinks is 12 multi choose 7, which is 12 plus 7 minus 1. Choose 12 minus 1, which is 18, choose 11. Then use calculator, we can get an answer.